Okay, so what if a computer processor wasn't a fixed piece of silicon? What if it was a floating collection of individual atoms that you could literally rearrange for every single problem? Well, that's not sci-fi anymore. It's the wild idea behind Amazon's Aquila, a new kind of quantum computer you can access right now. And in this explainer, we're going to break down exactly how this thing works.
I mean, think about the computer or phone you're using right now. At its core, there's a solid chip, etched with billions of transistors in a design that's totally permanent. It's been that way for decades. But what if we just threw that whole playbook out the window? What if the processor itself was fluid?
And again, this is not science fiction. This is the core concept behind the Aquila quantum processor. Instead of a static silicon chip, it uses 256 individual atoms held in place by lasers that can be totally reshuffled for every single problem you throw it at it.
So how on earth do you actually build a computer out of lasers and atoms? I mean, really. Let's dig into the core architecture because it's just fundamentally different from anything else out there.
Okay, so they call it a Field Programmable Qubit Array, or FPQA for short. But here's what that really means. Imagine you have hundreds of tiny, microscopic laser tweezers. And with these tweezers, you can pick up, move, and place individual atoms in any pattern you can dream up. For every single calculation, you're essentially building a brand new, custom-designed quantum chip from the ground up. This reconfigurability, it's its superpower.
All right, so we've got this flexible grid. But what about the building blocks themselves? The atoms. Well, it turns out nature kind of handed us the perfect component for a quantum computer on a silver platter.
Aquila uses rubidium-87 atoms, and scientists love to call them nature's perfect qubits. And for good reason. Unlike man-made qubits, which always have tiny manufacturing flaws, every single rubidium-87 atom is a perfect, flawless clone of every other one. Plus, they can hold on to their fragile quantum state, we call that coherence, for over a second, which, believe me, is an absolute eternity in the quantum world.
Now, this is where it gets really, really cool. How do these atoms actually become qubits? Well, they've got two modes. First, there's the ground state. You can think of it as a sleepy, stable atom, just hanging out. It's perfect for storing information. That's your zero. But then, you hit it with a laser, and bam! It puffs up into this enormous, super-energetic Rydberg state. That's your one. And in this pumped-up state, it suddenly gets really interactive with its neighbors. And that interaction, well, that's where the magic really begins.
So, that magic I just mentioned, it actually has a name, and it's one of the most powerful and, honestly, kind of bizarre tricks in all of quantum physics. It's called the Rydberg blockade.
Okay, so here's the absolute key. When one atom puffs up into that giant Rydberg state, it basically creates this invisible personal space bubble all around itself. And get this, any other atom inside that bubble is physically blocked from also getting excited. It's like a cosmic, nope, this spot's taken. And this isn't just some weird side effect. It's a built-in, naturally occurring logic gate. It hardwires a rule into the system. If you pick me, you cannot pick my neighbor. This is the absolute foundation of how this computer thinks.
All right, so we've got these movable atoms and this funky quantum personal space bubble. So what? What can you actually do with that? This is where we go from the cool physics to solving some seriously tough real-world problems.
You know, that personal space rule turns out to be the perfect physical model for a whole class of incredibly hard problems. For example, imagine you're placing cell towers. You want to pick the absolute maximum number of locations to get the best coverage, right? But there's a crucial rule. No two towers can be so close that their signals interfere. Well, the Rydberg blockade is that rule, baked right into the physics. The excited atoms are your chosen towers, and the blockade automatically makes sure none of them are too close. And this exact same logic, don't pick two things that conflict, is vital for everything from building financial portfolios to scheduling complex logistics.
And it's not just for business optimization. This thing is basically a physicist's dream sandbox, because you can arrange the atoms in any geometric pattern you want, like a honeycomb or even a super rare Kagome lattice. Scientists can simulate exotic states of matter that we can barely imagine, like quantum spin liquids. These are bizarre phases of matter that could be the key to things like new superconductors, but they're basically impossible to create or study any other way.
And look, this isn't just a theoretical playground. A massive paper in the journal Science in 2022 put this exact kind of machine head-to-head with a powerful classical computer on a very specific, very nasty problem. And the result? The quantum machine found the best answer more often. It was one of the first really clean, practical demonstrations of a genuine quantum advantage.
But there's a massive elephant in the room for all quantum computers.
And this next part, it tackles that problem head on. And honestly, it might be the single biggest breakthrough the entire field has seen in years.
Okay, here's the dirty little secret of quantum computing. Right now, all of them are incredibly noisy. They are just so fragile, so sensitive to the outside world that the tiniest vibration or change in temperature can throw off the whole calculation and fill it with errors. This noise problem has been the single biggest roadblock to building quantum computers that can actually do something useful. Until now.
In late 2023, researchers using this architecture made a historic announcement, a processor with 48 logical qubits. Now hold on. 48 might not sound like a huge number compared to the hundreds or thousands of physical qubits you hear about, but that's the whole point. These aren't just fragile, noisy physical qubits. These are robust, error-corrected, logical qubits. And that changes absolutely everything.
So how did they do it? The strategy is just brilliant. Instead of relying on one single, fragile atom, they encode one powerful, robust, logical qubit across a team of physical atoms. They work together. And because this computer can literally move atoms around with laser tweezers, they can do something amazing. They can physically shuttle this team of atoms between the main processing area and a separate checkup zone. In that zone, they can actually check for errors in the middle of a calculation and fix them on the fly, without messing up the main program. This physical shuttling ability, it's a superpower that other types of quantum computers just don't have.
And this chart, this shows the money shot. This is the groundbreaking result. The experiment proves something absolutely crucial. See, the error rate for a single, unprotected physical qubit is pretty high. But when they built a logical qubit protected by its team of physical atoms, its error rate was way, way lower. This was the world's first proof that this kind of error correction actually works in the real world, that adding more physical parts to correct errors makes the whole system more reliable, not less.
So this incredible breakthrough, it's not the finish line, not even close. It's the starting pistol for an insanely ambitious race towards building truly useful, fault-tolerant quantum computers.
And Aquila, the company building these machines, has put out this incredibly bold public roadmap. And just look at these numbers. The pace is just staggering. We go from 256 physical qubits today to over 3,000 next year, and then over 10,000 by 2026. That is not just steady progress, folks. That is an explosion in computing power. And it's all laser-focused on hitting that magic number of about 100 stable, logical qubits. That's the milestone that could really unlock the next era of computing.
Now, a huge milestone on that roadmap, set for 2025, is something with a wild name: magic state distillation. The easiest way to think about it is like this. To run any possible quantum algorithm, the really powerful universal ones, you need a few very special ultra-pure quantum states. They're like the special ingredients for a really complex recipe. Magic state distillation is the process for creating those perfect ingredients. Nailing this would basically unlock universal quantum computation on their error-corrected machine.
And all of this brings us to the ultimate question, doesn't it? We've seen how this incredible technology works, from its amazing reconfigurable atoms all the way to its game-changing error correction. We're literally watching it evolve from a noisy experiment into a fault-tolerant reality. So when a stable 10,000 qubit computer built on these very principles finally arrives, what impossible problem will we solve first? Will it be a new life-saving medicine? A revolutionary new material? That question, that's what's driving this entire field forward at lightning speed.